Hey guys, it's Nicola from Calcunic, and today we're going to be talking about counting with repetitions. Let's get right into it. Instead of directly starting with some formula or definition, let's start with an example and see if we could get a feel for these types of problems. So first we're asked to find the number of arrangements of the word stats. Well, how you would usually solve this is to notice that the first S could go into either the first, second, third, fourth, or fifth spots. So that's 5 options for the first S. The first T can fit in any of the remaining 4 spots, so we multiply this by 4. The A could fit into any of the 3 remaining spots, so times 3. The second T could fit into any of the 2 remaining spots, and the last S goes into the last spot. This is equal to 5 factorial, written as 5 exclamation mark, or just 120. However, we have the case that we have 2 S's and 2 T's. And so out of this 120, we're going to see a few duplicates. If you're not convinced, let me show you an example. Suppose we want to build one of our 120 arrangements of the word stats. Let's do it like this. Say the first S goes into the 4th spot. The first T goes into the 3rd spot. The A goes into the 5th spot. The second T goes into the 2nd spot. And the last S goes into the 1st spot. Now we'll build it another way. Let's say the first S goes into the 1st spot. The first T goes into the 2nd spot. The A goes into the 5th spot. The second T goes into the 3rd spot. And the last S goes into the 4th spot. Well, it turns out that we have the same arrangement, STTSA. However, we got to it in 2 different ways. And so we know that out of the 120 arrangements that we counted, there are going to be some duplicates. But exactly how many duplicates? Well, we could see that the reason we're getting duplicates is because we have 2 of the S's and 2 of the T's. And the number of ways that the 2 S's and 2 T's can be arranged is 2 factorial times 2 factorial, or simply 4. This is because the 2 S's could be arranged in 2 ways, and the same goes for the 2 T's. If we had, for instance, 3 S's, it would be 3 factorial, as 3 letters can be arranged in 6 different possible ways. 3 factorial. So to get the desired answer, it's not just 120, but it's 5 factorial over 2 factorial times 2 factorial. This is equal to 120 over 4, or simply 30. So we were able to find a pretty convincing pattern here to count the number of arrangements when there are repetitions. Let's see if we could write a more general formula to describe this relationship. If we wanted to define what we just discovered, we could say that if we are given a string of symbols A1, A2, all the way to AN, and N1, N2 to Ni are the number of repeating symbols in that string, then the number of arrangements of the symbols in that string is going to be equal to n factorial all over N1 factorial times N2 factorial all the way to Ni factorial. Now, if this language is confusing you, don't worry. Let's go back and look at the stats example we were just looking at. In this case, our string of symbols is STATS, where A1 is S, A2 is T, A3 is A, A4 is T, and A5 is S. Furthermore, because the letters S and T repeat twice, we'll have that N1 is equal to 2, and N2 is equal to 2 as well. And now we could do our final calculation to find the total number of arrangements. We have 5 factorial over 2 factorial times 2 factorial, just like before, and once again, this is equal to 30. Let's see if we can apply what we just learned to some examples. We're asked to find the number of arrangements of the word statistics. What would have seemed like a pretty difficult problem becomes really straightforward. All we have to do is remember the formula we derived before. In the word statistics, there are 10 letters, so we have that n is equal to 10. Furthermore, the letter S repeats 3 times, so we could write n subscript s, just to remember which letter it is equal to 3. We have the letter T repeating 3 times, so we could say that n of T is equal to 3 as well. And finally, the letter I repeats twice. And so if we plug this into our equation, we'll get that the number of arrangements is n factorial, or 10 factorial, all over the number of repetitions, which in this case is 3 factorial times 3 factorial times 2 factorial. And some quick mental math will give us the final solution, which is 50,400. We finished this video off with a word problem. Say there are 4 people on a bus with 5 stops. We're asked to find the probability that 2 people get off stop 1 and 2 people get off stop 4. Well, because we're being asked to find the probability, the first step is to find the number of total possible outcomes. Because each of the 4 people are unique, and they could each get off at any of the 5 stops, we have 5 to the power of 4 total outcomes. Now, how can we find the number of outcomes given our specific restrictions, where 2 people get off stop 1 and 2 people get off stop 4? To help us solve this, let's draw a small picture. In this picture, we have 4 slots, representing the order that the 4 people will get off the bus. The number of ways we can arrange 4 people is 4 factorial. However, in this case, the order of people getting off at each stop does not matter. The only thing that matters is at which stop they got off at. Here we have 2 slots of 2 spaces where order does not matter, and we could think of these as repetitions. So, from the formula we derived before, the total number of arrangements that fit our restrictions is 4 factorial over 2 factorial times 2 factorial. If we put all of this together, we get that the probability is equal to 4 factorial over 2 factorial times 2 factorial all over 5 to the power of 4, or simply 6 over 625. Alright guys, thank you so much for watching. If you had any questions or other video suggestions, drop them down in the comments below. I do try to get to all of them. And if you feel like you learned something, if you saw something cool, or if you just like what you saw, then consider leaving a like and a subscribe. I would really appreciate it. It would help me grow my channel. And yeah, that's all from me. Till next time.